talking about Linux files and directories. We have another topic next week that we will be looking at Linux permissions, and then we're going to jump back to C for a while. So we are getting back to C soon. So in this topic, we're going to look at some general concepts related to files and directories. We'll be looking at the file system a little bit to understand a little bit better how that's structured. Talk about some concepts related to paths and directories. That's mostly review. We will look at links, so hard links and symbolic links, how to find files. Again, some more general concepts related to files and file names, and then we'll look at wildcards and quoting at the end. So we understand the concept of a file. It's a named container for our data. And then we have the blocks of each file that are stored on disk. And the operating system, when you create a file, it maintains a special data structure for each file, for each directory, called an index node, an inode. So this is a data structure that's stored in a special part of the disk by the file system, and it contains metadata about each file. So you've got things like a unique identifier, the inode number. You've got the file size. You've got who owns it. So we're going to talk about Linux permissions in the next topic. And we're going to see that, okay, you can have a user owning a file, but you also can have a group owning a file. So who owns it? What permissions have been put on it? We call that the mode. And again, we'll see that in the next topic. So is it readable? Is it writable? Is it executable? And so on. We've got timestamps, when it was created, modified, last update, or last accessed, I should say. And then we're going to see later, it also stores the number of links to the file. We'll see what that means a little bit later in this topic. And then finally, it's got pointers to the various blocks on disk where that file's content is actually stored. So that might be one block if it's a tiny little file. It might be a ton of blocks. It's got all of those pointers within the inode. So if you want to view an inode, you can use the stat command to display a file's status. So for example, if I've got a file hello.c here, I can say stat hello.c, and that gives me some information that has been read from the file's inode. So what can we see here? We can see its inode number, again, a unique number identifying this file. How many blocks it's using, the file size, we can see who owns it, so the user ID, the group ID. Again, we're going to talk about all those in the next topic. What permissions that have been associated with it, and then of course the timestamps and so on. So if you want to view inode information, you're using the stat command. You can also view information about a directory. So if I said stat/user/bin, same idea. There's an inode for everything in the Linux file system, whether it's a file, a directory, a link, whatever. So same idea here. We've got an inode number. We've got the size. Bottom line is every file or directory in the file system has an inode. OK, so looking at the types of files that we have in the file system, we of course have regular files, which are comprised of a sequence of bytes. We generally will distinguish between a text file and a binary file. So text files contain printable characters and white space, generally between ASCII 32 and 126 or 127. So if we pull up our trusty ASCII table, you can see that ASCII 32 is the space, and then after that we've got some special characters, we've got the digits, all of the letters, and then going down to 126 is the tilde. So that's generally going to be the content of a text file, along with some of the control characters, like we've got tab here and line feed and so on. On the other hand, a binary file can use any of the bytes from 0 to 255. And if you try to cat a binary file, you're just going to see gibberish because it's using non-printable characters. Okay, so if I were to go and say cat/bin/ls, it just gives me gibberish. Sometimes you'll accidentally cat a binary file and it will screw up your terminal. And you'll start typing and you won't actually see letters. You will actually see it'll start just printing out binary gibberish. I can't get it to do that right now. Of course, it doesn't want to do it for me when I want it to. But if that happens to you, you start typing after catting a binary file and you just see gibberish, you can either type stty sane, that might fix it for you, or you can type reset, and that should fix the problem for you. And if it doesn't, you just close your terminal and you SSH back in. Now, directories are also files. Everything is a file in Linux in terms of the file system. So directories are also files. A directory also has an inode that points to its data block on disk, to its file on disk. The difference being with a directory, its file on disk is not, content that we can edit. It is a table that maps the directory entries, so the file names, to their inode numbers. Okay, so again, we said each file has an inode. Each inode has a unique identifier. And so the directory file maps each entry in the directory to its inode number. So when you do an ls-l, what it's doing is it's going and getting the directory's inode. That inode has got a pointer to the directory's file, which has that table there. And so for each of those entries, it's going to read the inode for that entry using the stat system call. So there's a stat command, but there's also a stat C function that we can call. And so it'll read the entry's inode to get that file's inode or that subdirectory's inode, and then it prints the information from that inode to the screen here. So just to show you here, if we remember our man page section, so man1, section 1 was for commands. So if I do man1 stat, that gives me the man page for the stat command. If I do man2 stat, that was for C libraries and system calls, that gives me the man page for the stat C function. So in this case, ls would be calling the stat C function to read the inode of a file. Okay, other types of files. We've got device files, which are special files that represent devices, where it could be your sound card, it could be some USB key that you plugged in. I think you guys are old enough to remember CD-ROM drives, right? So it used to be if you had a CD-ROM in your computer, you would find the CD-ROM in /dev/CD-ROM. It was a special file that represented your CD-ROM. And the idea here is that it provides a uniform experience, consistency to our program. So just as I would call certain system calls on the system, functions like open and read and write to read and write from a file, I can do the same with devices. I can call the same system calls on my CD-ROM that I would on a regular file, because everything is represented as a file in Linux. So our devices are typically found in /dev. You generally won't be in this directory often, but we'll see things like, well, we're going to see /dev/null. That's used often. /dev/random. That's used to get random numbers. Just trying to find a good example of. Okay, so these are the hard drive partitions on this server, /dev/VDA1, VDA2, and so on. Again, if you had a CD-ROM drive, you would see /dev/CD-ROM in there. So again, we're using special files to represent devices. Links, we're going to talk about links in a few minutes. So we can have hard links or soft links. A hard link allows us to create basically another file name for the same file, whereas a soft link or a symlink, a symbolic link, is used to create a pointer to another file name in the system. And it's similar to Windows shortcuts. We'll see how they differ in a little bit. We can have FIFOs, so first in, first out. It's basically a named pipe that allows two processes to communicate. So as an example, I have this special file, mypipe.fifo. If I do a stat on it, it tells me it's a FIFO, first in, first out. So let's do an example here. I can have, let's just write a little one-liner, and again, you don't need to be able to know this or understand what I'm doing, but what I'm going to do is just write a little script here that is simply going to run the date command, and it's going to redirect its output into that pipe. And then we'll sleep for 1 second and we'll loop. Okay, so you've got one process that's writing into the pipe, and then we have another process. I'll use tail-f, which is the follow option. It allows you to read the bottom of a file and then keep reading it. So tail-f on the pipe, And now you can see that it starts reading that data that this process is sending into the pipe. So it's a means of unidirectional inter-process communication. We want one program on the system to talk to another program. We can do it through a FIFO, through a pipe. Again, you don't need to know how to set these up or anything like that. I just wanted to demonstrate that special file type. Another one for inter-process communication is a socket. So just like I can send data to a server over the network, I can also have a server create a special file called a socket. So when I run this server, I just wrote a little program in C that creates this socket, and it starts listening on that socket, just like it would listen on a network connection. So it's a special file that it's listening on. And now we can have another program write data to that socket file and communicate with the server through that. So if I say, I don't know, hi server, then what happens is the client writes the data to that special socket file. The server is reading from that, so it receives that message, and then the server writes its reply back through that socket file, and then of course the client receives it. Okay, so it's another way for two processes on a system to communicate, inter-process communication. Okay. So those are the main file types on a Linux system. If you want to view the type of a file, generally when you type ls, you see an indication of the file's types based on the color. So green is an executable file. We've got blue for directories, cyan for links, yellow for pipes, and so on. That's only because if you type alias, on most systems you will see that ls is aliased to ls-color. So when you're typing ls, it's actually entering this, --color equals auto. On some systems, that alias might not be set up, so you might actually just see this. If you want color or you want to see an indicator of each file's type, you can either say ls-color, and again, that distinguishes the types based on color, or you can say ls-F. And that will give you a special character. So star is an executable file, slash is a directory, the @ symbol is a symbolic link, we've got a pipe, a FIFO pipe, socket file, and so on. Okay, so ls-F. All right, so this is, we've already looked at this. We saw in topic 1 that the Linux file system is represented as an upside-down tree, which has a single root, and then of course we have multiple levels descending from that. So the top level directory is called the root directory, not to be confused with /root. Right, this directory here, this is the root user's home directory. When we talk about the root directory, we're talking about the top level, the root of the tree. So, not a trick question, just want to make sure we understand basic file system navigation. If I wanted to change to the root directory, what would I type? Somebody just yell it out. cd/, good. Okay, so again, cd and then where we want to go. So if we want to go to the root directory, we just type cd/. Okay, this is going to put you to sleep, and I apologize for this. The Linux File System Hierarchy Standard, or the FHS. So the idea here is that back in the day, you had all of these Unix variants, and all of the vendors had a slightly different layout to their file system. So you go into one vendor's variant of Unix, and okay, they've got their set of directories that they use. But then you go to another one, and maybe they have a slightly different layout. And so that made for a learning curve. You couldn't, just go on a system and, okay, we've got this standard set of directories on every Unix system, because they might have been a bit different. So in 1994, they created the Linux File System Hierarchy Standard, which was intended to standardize, at least at the very top level of the file system, the directories that you can expect to find on any given Linux system, no matter what distro it is, and what their purpose is. And so now it's maintained by the Linux Foundation. They're up to version 3. I'm not going to go through all of this, but we'll just sort of go through the major highlights here. And so we'll just get an understanding of it. Reason being that, again, when you log into a Linux system, you're going to see all of these directories. So it's a good idea to at least have a working knowledge of what they're for and where you might find certain things. So on a Linux system, in /bin, you will find all of the commands, the user commands. So things like ls, cp, make dir, and so on. It used to be that bin and user bin were separate. Nowadays, you can see that bin is just, it's called a symbolic link to /user bin. So if you go into /bin, you're actually going into user bin. So that's where all of the user programs are found on a Linux system. The boot is where the kernel is stored, so that's used to boot up the computer. We saw dev for device files. etc is for the system configuration. So you're going to find all of your Linux configuration files on here. If I wanted to configure, say, the host name of my system, I would edit /etc/hostname. If I wanted to schedule jobs, I could edit the cron tab. So this is a special file that allows me to say, okay, at minute 0, hour 0, on every day of the month, every day of the week, I want to, I don't know, back up my etc directory to the backup directory. And so what this will do is it will, every single day at midnight, it's going to make a copy of my etc directory to backup. So cron tab is a way we can schedule tasks on a Linux system. So there's a ton of other configuration files in here, but the bottom line is most Linux config files you will find in /etc. Okay, we know about home. Yeah, opt is another location where if I install like a package from IBM, it usually won't go into user bin, it'll go into /opt. sbin and user sbin, these are for system administration commands, so commands used by the root user. So I can see things like user add to create users, user del to remove users, and so on. The temp directory, so temporary files, anything you write into the temp directory gets cleared every time you reboot your computer. So you don't want to put anything in there that you want to keep. And then we have the user hierarchy, which is intended to be read-only data. So for example, we saw user bin for commands. The idea here, we're saying it's read-only. So we don't want to go in, let's say I compile some software and I want to install it on my system. I don't want to put it into user bin, because user bin is being updated by my package manager. So when I install a package on my system, it puts it into user bin for me. If I'm also messing with user bin, I could screw things up. I could overwrite packages that the package manager installed. So it's intended to be read-only. Similarly, like user lib64. Okay, this is where your system libraries are located. Things like libc. So the C standard library is located in user lib64. We have user sbin, I said, for system administration commands. And then we have user local. So this is the same kind of hierarchy. We have user local bin, user local lib64, user local sbin. So it mirrors the user directory, but the idea here is that this is for local, site-specific information. So if I want to compile my own code and install it, I don't put it into user bin, I put it into user local bin. And that then won't clash with software installed by the package manager. Finally, we have the var hierarchy. So this is for variable data. It's for data that is expected to change. So if we go into var, we have things like var lib. If I installed, say, like the MySQL database, a very popular database server, you would find its database files under /var/lib/mysql. Okay, so again, it's variable data that's expected to change. Similarly, another one that we use often is var log. Now, I can't access most of these right now because you have to be root. But if something was going wrong with a system or it's slow and I want to figure out what's going on, I will log into the system. I'll take a look at, I'll cd to var log. And I'll take a look maybe at messages, varlog messages, which is one of the main system log files. Okay, so that is the Linux file system hierarchy standard. Again, a standard set of directories that you can find on every Linux system. if we compare the Linux file system to Windows, on Windows, each hard drive is assigned a different drive letter. So the C drive, the D drive, and so on. So if you've got multiple hard drives in your computer, you're going to have multiple directory trees, multiple hierarchies. So example here, I've got 2 hard drives in my computer. We've got the C drive, that's one directory tree, and then we've got the D drive. 2 different directory hierarchies. Now on Linux, they do things a little bit differently. So you've got a single unified hierarchy that could potentially span multiple disks. It could even have, it could span across computers. So you could be accessing remote file systems within your hierarchy. So we say that a disk, whether it's a local disk or it's a disk halfway across the world on some other server, that we mount them at specific directories in the directory tree that we call mount points. So as an example, on compute.gol, your home directory is not actually stored on compute.gol. It's on a separate server on the computer science file server, and it gets mounted under /home/whatever your username is. Another example here, we've got this /var, which is located on a separate hard drive, and it is mounted, the partition that it's stored on gets mounted as /var in the file system. So as the user, we don't need to know, we don't need to care where things are physically stored. If it's on the C drive or the D drive or whatever, if it's on some server across the world, we don't care. We just work with this single unified file system hierarchy. So one way you can see the file system mounts, and you can see also disk usage, so how much disk you have left or disk space you have left, is the df command, so disk free. So if I just type df, it's going to give me a list of all the file systems and where they are mounted. So here you can see the root directory is mounted from a partition called /dev VDA5, so one of our hard drives. We've got all kinds of home directories. So if we just look at mine, you can see that my home directory, home JSONs4, has been mounted from the computer science file server from a directory called /data cs homes JSONs4. So it's on a completely separate server. It could be all the way across the world, and it's been mounted on this server as though it just exists on this server as home JSONs4, as though it's just another regular directory on the server. If you want to see your disk space or your disk usage with human readable sizes, you can do df-h, and now you can see things like, okay, on the root disk, we've got 7.3 gigs used, 32 gigs free. For our home directories on the server, we've got 6.4 terabytes used and 31 terabytes free, and so on. Okay, so df-h. If you wanted to see the file system types being used, you can use -t. So I could say th for show me the types and give me human readable sizes. So we can see for everyone's home directories, it uses this NFS4 file system type, which is the network file system. It's accessing the file system hierarchy over the network. On our root directory, we're using another file system type called btrfs. On /boot, so the directory that is used to boot the computer, another one called ext4. The details of these are not important. It's just if you wanted to look at the different file system types on your system, you can use df-T. Now, this is all review. We saw in topic 1 the difference between absolute and relative paths, so hopefully that is fairly clear to everyone. Again, an absolute path just starts at the very top of the tree, and so it will start with a /, whereas a relative path is going to change depending on where we are in the file system. It is relative to our current location. Okay, we also saw these special directory references. So dot again refers to the directory itself, and dot refers to the parent. And now that we know about inodes, we can sort of understand a little bit better that, okay, so in the directory file, we've got the file name dot, and the inode number is the inode number of that directory itself, right? It's just pointing to itself. Whereas dot would point to the inode of the parent directory. So again, not a trick question, just making sure we understand basic concepts. How would I see these special references in a directory? What would I type? How do we list the contents of a directory? ls, and what do we pass to ls in order to see things that start with dots? -a, right? So I can do ls-a, or I can see ls-la, right? And that will show me any files. Again, we said by default in a Linux system, any files that start with a dot are hidden by default from ls, but if we pass -a, that shows me all files. Okay, and of course we saw our home directory that tilde can be used as a shorthand to stand in for /home/ whatever my username is, whereas tilde user is a shorthand for /home/ whatever that user's username is. Now, one thing we did not see is that the shell also maintains a special environment variable. We're going to learn about environment variables a little later in the course, but there is a special variable called $home that will always hold the path of your home directory. Okay, so you can also, I could say echo home, and that shows me the path of my home directory. So if I am logged in as the user Abby, and I'm currently in /home/Abby, all of these are equivalent in order to access file1 down there at the bottom. Okay, so I could say temp/file1, I could say dot/temp/file1, so current directory /temp/file1, tilde/temp/file1. Again, tilde is home Abby /home/Abby, so /temp/file1, $home temp file1, and then of course the absolute path /home Abby temp file1. That should all be review, but just wanted to quickly revisit that. So in order to interpret a path, you look at the first character, you say, okay, is it a slash? If so, we're starting from the root of the tree. So /home Abby temp file1. Is it a tilde? If so, we're starting from a home directory. So /home/ whatever my username is, or if it's tilde user, then whatever that username is. If it's a dot, we're starting from the current directory, dot/temp/file1. If it's a dot, starting from the parent, dot/Abby/temp file1. Otherwise, it's going to be from the current directory. From that starting point then, you descend into each subdirectory in the path. So I go into temp, and then I've got to file1. So you just keep descending into each subdirectory until you complete the whole path. Okay, so notion of the directory stack. We've got these two commands, pushd and popd. What they allow you to do is sort of navigate around the file system and remember where you've been so that you can easily get back. It's kind of like walking through the forest and leaving breadcrumbs and then following your trail back. I could say, for example, pushd user bin. What that does is it changes me to user bin, and it puts it on the directory stack. And you can see that my previous directory, tilde, is on the directory stack as well. I can now say pushd, say temp. That changes me to temp, and it puts that onto the stack as well. Okay, so I could do that a few more times. I don't know, var lib. And then when I want to get back, I say, so I'm currently in var lib. This is the contents of my directory stack. So I just say popd. Now that's going to pop this off the stack and change to the new head. So it'll take me back one directory. If I do pop, so I'm now in /temp. If I do popd again, pops off the top of the stack, and it takes me back to the new head of the stack, which is user bin. Do another popd, takes me back to my original home directory. Okay, so it's not something I use often, but it can be handy if you know that you need to change around to a bunch of directories and you want a quick way to get back. Instead of using cd, you can do pushd in order to change to those directories, and then popd to get back. Okay, so I've put this in as an exercise. I'm not going to go through this right now, but I've left it as an exercise for you. I've also put in the solutions here. Just some basic, a basic skills roundup to ensure that you can sort of make sure that you understand how to navigate around, that you understand absolute and relative paths. So I recommend checking that out at some point. You can use that, when you're studying for the midterm or whatever. Try to avoid looking at the answers. So just look at the instructions and then check your answers at the end using what I've provided there. Okay, let's talk about links. So Let's suppose that I create a new file, hello.c, in /home/Jeff. We say that the file name hello.c is a hard link. In other words, it's a pointer to that file's contents on disk. If we want, we can create additional hard links to that file's contents, using the ln command. So I could say ln, I want to create a new link to this file hello.c, and I want to call it program.c. And so what that's going to do is just basically have now, we've got two file names to refer to the same content on disk. They both point to the same content. We haven't made a copy of the file, but it now has two file names that we can use to refer to it. So, of course, because they point at the same content, if I edit the file through one, then of course we're going to see the changes through all of its links, through all of the file names. All right, so I've got my file hello.c. And I want to make a link to it, so I'll say ln hello.c, and what I want that link to be called. So let's call it program.c. And if we take a look at ls, you can see that, okay, it's created program.c. Doesn't look any different. There's nothing special about it. It just looks like a regular file. But if we take a look at, well, if I edit program.c, for example, and let's say we'll make it return 1, and then I look at hello.c, right? I just edited the same file. I'm just editing it through a different file name now. So it's called a hard link. Now, at the file system level, understanding what's going on here, we saw earlier that when we create a file, the file system maintains that special data structure that it calls an inode. Okay, so we created the file hello.c, so an inode got created for it. It was given a special inode number, a unique identifier for that file. And you'll notice that its link count was set to 1 because it only has one file name, hello.c, to start with. And then the inode, of course, points to its data blocks on disk. Now, the inode for the directory that contains the file also gets updated when we create the file, right? So we have to open up the inode for, let's say, /home/Jeff, if that's the directory that we're creating the file in. It gets the directories file, which again we said was a table mapping the entries of the directory, the file names in the directory, to inode numbers. And so what it then does is it puts in, okay, a new entry for hello.c, which points to that inode number that was created for the file. Okay, so the directories file links that file name to its inode. Suppose now I create my new hard link. I create a hard link program.c that points to hello.c. In this case, again, we edit the directories file. We add that new link, program.c, and you'll notice that we didn't make any copies. There's no new inode. It's just pointing at the exact same inode as the original file, right? Same content on disk. And you'll notice that the inode of the file gets updated as well. The link count is now set to 2. You can also see this if you look at ls. So we had kind of glossed over this when we originally looked at this in topic 1. But in the ls-l output, you can see this column here. This is the number of hard links that a file or directory has, or file has, I should say. So you can see for program.c, it's got 2 links. Hello.c has 2 links because we've got 2 file names pointing to that. Okay, so you can see that with ls. Now, when you run the rm command, let's say I delete the original file name. When we delete something, the official terminology is actually unlinking. We are unlinking the file. And now we understand why, because file names are links. They are hard links to the file's content on disk. So if I delete that original file hello.c, it simply removes that link. It unlinks it from that file's content. But the file is not deleted because it's still accessible through the second link that we created, program.c. So as long as the link count is greater than 0, that file doesn't actually get deleted. So again, looking at unlinking through at a file system level, I deleted hello.c, so my directory file gets updated, and that hello.c entry gets deleted from the directory file. But of course, because we still have the program.c link in that directory, and it's linking at that original inode, then that file is still accessible. The inode for the file also gets updated. The link count gets decremented to 1. Now, suppose we delete the last hard link to the file. So what's going to happen here is, again, the directory file gets updated, so it removes that link from there. It updates the inode for the file. The link count is now updated to 0. We have no more links left to that file. And so because the file's link count is now 0, it deletes the file's inode, and so the file is effectively deleted. In reality, on disk, the file is probably still there. It's probably kicking around. The file system's not going to immediately overwrite it or zero it out, but it's no longer reachable. We have no links to it anymore, so it's effectively deleted, and the file system will mark that space as being available so that when we do another write, if we create another file, that can now be overwritten. Okay, so that's hard links and unlinking. Now, symbolic links, also known as soft links, I don't think anyone calls them soft links. You generally will hear them called symbolic links or sim links. These are another kind of link that is similar to a shortcut in Windows. So with hard links, we had two file names pointing at the same content on disk. Whereas with a sim link, instead of pointing directly at the content on disk, it's an indirect pointer. It's pointing at another path name, at another file name within the file system. So we create it using ln-s. So we've got our hello.c. I can make a symbolic link to it by, again, saying, okay, what's the target of my link? I want it to point at hello.c. And what is the link name? So program.c. Now if we take a look, you can see ls gives us this special notation. It's program.c that is pointing at the file name hello.c. So ln-s for symbolic link. So again, at the file system level, what's going on here is when I create that symlink, once again, the directory file gets updated with the new entry, program.c. But this time, we're creating a brand new inode for that symlink, for that symbolic link. And so the symlink actually has the target path in it. So it says, okay, I'm program.c and I am pointing at the file name hello.c. And then hello.c in turn points at the file's content on disk. And that's why we call it an indirect link, because it's not pointing directly at the content, it's pointing at another inode, which then points at the content on disk. So yeah, I showed you when we view a symlink with ls-l, you'll see that notation there with the arrow that just says, okay, program.c is a symlink that points at hello.c. We can also use symlinks to directories. So you can't do that with hard links, but you can do it with symlinks. So if I wanted a copy of user bin and I want it convenient and accessible to me in my current directory, I could say, all right, I want to create a symlink to user bin, and I'll call it bin in the current directory. And if we take a look at that, I can cd into that. I can see all of my commands there that I would see if I were to change to cd user bin, because that's what I just did. I just accessed it through this symlink bin that I've created. So this is useful for, sometimes you'll install like a bunch of packages on a system. So I don't know, maybe like a C compiler, or maybe for people doing GPU work, we install a library called CUDA. And you'll have a bunch of different versions of like, it'll be like CUDA, I don't know, 8.0.0, and we'll have like CUDA 9.0.0, CUDA 10, and so on. So you've got this library that has you have a bunch of different versions of this library on your system. And you want to be able to tell people, all right, just go to this directory for the current version. What you can do is often we'll create something like, I don't know, CUDA-current. And that'll be like CUDA 10 or something like that. And so then you can tell someone, all right, if you want a specific version, you can go into there. But if you just want the current version, you can go to, /user lib CUDA-current. And that is a symlink that is always we will maintain it and point it at the current version of CUDA. And then if we were to install a new version of it, we would update that symlink and point it at the latest version, so that the user can be assured that whenever they use CUDA-current, they're going to be using the current version of that software. So that's just one use of where we sometimes use symlinks to directories. Now, if you change to a symlinked directory, when you type pwd, that's actually a built-in command in the shell. So it's going to lie to you. So if I go, remember I said, let's get rid of all my CUDA stuff here. So I made a symlink to user bin called bin. If I change into that and I type pwd, that is lying to me. That's telling me, oh, you're still in your home directory in this directory called bin, right? It gives you the symlinked path. If you want to know the actual path, you can run /bin/pwd. And that gives me the actual path that I'm in. I'm in /user/bin. Now, in terms of unlinking, when we're dealing with symlink, so deleting, when you delete a symlink, the original file, of course, is not going to be deleted because the symlink is just a pointer to the file name. So here we've got program.c pointing at hello.c. If I delete program.c, then of course that's not going to affect hello.c because it was just like a shortcut to it, right? On Windows, you've got shortcuts to programs and files. That's basically a shortcut to that file name. However, if we delete the original file instead, and we have a symlink to it, then that link becomes a broken link or a dangling link. So again, I've got my link restored. If I delete this original file, hello.c, and we take a look at ls, you can see it's in red now because it's pointing still at that hello.c file, which no longer exists. We deleted it. So it is a dangling link. Okay, so the ln command. ln, whatever you want the target of your link to be, and then your link name. That will give you a hard link, and if you use -s, you will get a symbolic link, an indirect pointer. Yep. Sorry, can you edit it? Yes, absolutely, sure. So I can't now because I deleted it. It's now a dangling link. But if I were to copy that file back or recreate that file, that link gets restored. And so if so I've got program.c, it's a symlink to hello.c. If I edit that, it's just like if I were typing, you know, if I were editing hello.c, it's going to point at that file. So if I say, I don't know, return 99, oh, whatever. So now if I look at hello.c, yeah, it's the same content because it's pointing at that file. So yes, you can. Yep. Any other questions about that? Okay, so ln to create a hard link, ln-s to create a symbolic link or a soft link. So summarizing the differences between the two, again, a hard link is a direct pointer. It is basically a second file name for a physical file on disk, and it points directly at that file. They point to the same inode. Whereas a symbolic link is an indirect pointer. It is basically pointing at another path, at another file name. So it's got its own inode. That inode stores the path that it points to. Yeah, so we said that the inode is shared for hard links. We have a different inode for symbolic links. In terms of visibility, hard links don't look any different, right? They just look like another file in the directory. The only way we sort of knew that we had a hard link there was when we typed ls-l, we saw that the hard link column had increased, but otherwise we wouldn't know that, oh, this is a hard link. It's because a regular file name is a hard link, right? Whereas a symbolic link, of course, appears distinct. We saw that notation with ls where it showed a little arrow that this is pointing at this file. In terms of storage, I mean, it's minimal, but hard links use a little bit less storage because you don't have to have that extra inode. They're both pointing, we have two names pointing at the same inode, whereas a symbolic link requires, of course, that extra inode. When we delete a hard link, the file remains accessible until we've deleted all of the hard links. With symbolic links, if we delete the symlink, that original file is unaffected, but if we delete the original file, then the symlink becomes a dangling link. File systems, yeah, so hard links only work within the same file system. So if I've mounted, you know, /home from some other system, I cannot create a hard link from one file system into another file system. You're not allowed to do that. With symbolic links, that's no problem. You can do ln-s, you know, whatever, from one file system to another. Not an issue. So limitations of hard links, again, we cannot hard link directories. You can only hard link to files, and you cannot hard link across file systems. Symbolic links, you can create a symlink to a directory. You can symlink across file systems, no problem. And then, of course, we require the target's file path to be valid. So once again, if I were to delete hello.c, that becomes a dangling link. OK, any questions about that before I move on? In terms of practicality, I don't remember a time in my career when I've had to actually create a hard link. Okay? Generally, I use symlinks all the time. Hard links are fairly uncommon. They are used by some tools. Like, I know some backup tools will create hard links of a given directory tree or a given set of files, I should say, so that they can sort of mirror a directory tree and provide a backup location without copying the actual content and making a duplicate of it. So that's one area where I've seen hard links used. In terms of my actual practice, I've never had to use hard links, but I use symlinks all the time. Nevertheless, understanding hard links is important because, again, a hard link is just a file name. So it helps us to understand, well, what's going on with file names, what's going on when we create a file and when we delete or unlink a file. OK, finding files. So I looked at my laptop last night and found that it has over 2.2 million files on it, just on the Linux part of things. So the question then becomes, well, what if I need to find one file? Obviously, it's not feasible for me to CD around my file system and use ls in order to find something. So instead, I use the find command. So by default, if you type find, it's just going to perform a recursive search of the current directory tree. So just like the tree command shows you the current directory tree, find does the same thing. It just doesn't do it with nice pretty colors and lines and everything. So features of the find command, you can search using wildcards. So if I don't know the names of my files, or if I want to find multiple files, I can use a wildcard. So I can say something like star.c, and that will find all C files, all files that end with an extension .c. I can search using file attributes. So I could search, show me all files that are greater than 1 gigabyte in size. That's a useful one when you're running out of disk space and you need to find some big files to delete. You can use find for that. You can find files based on their owner, based on when they were last modified, all kinds of different attributes. You can also use find to execute commands on the files that it finds. So you can tell it, all right, I want you to find all JPEG files. Let's say I'm a photographer, I want to back up my images. So I can say, OK, find all files that end with the extension .jpg. And when you find them, I want you to run the move command and move them into a given directory. OK, so find is useful for that as well. So as I say, if I simply type find, that will give me a recursive search of the current directory tree. Alternatively, I can specify the starting point. So I could say find /, and now that starts at the root directory. If I wanted to find, say, all files named stdio.h under user include, I can say find. So my starting point, user include. I want to find files. So I'm going to say type F. And I want to find files named standardio.h. Now, if I did this, if there was a file named like standardio.h, whoops, in capital letters, this would not find it because this is a case-sensitive search. If I want a case-insensitive search, I use iname. Okay, and that's the one I just happen to use all the time whenever I do a search. That way it just finds anything, it doesn't matter, you don't have to worry about capitalization. So I recommend just always searching with iname. And so you can see now it scans the directory tree rooted at /user include, and it shows me all files that are named standardio.h. If I want to find all files that end with .c under the current directory tree, same sort of idea here. So I'm going to say where I want to start my search, or I can just leave that out if I want, and by default it will start in the current directory. I want to find all files, so type F, and we're going to say star.c. Now I have to put that in quotes. We're going to see a little bit later in this topic why. But that is saying find any file that ends with .c. And now that shows me all of the C files in my directory tree. So wildcard characters, The star is going to match any sequence of characters. So for example, H star O would match the word hello. So any sequence of characters. The question mark matches a single character. So if I have H question mark LLO, that's going to match the word hello. And then any characters between those square brackets, it's going to match any of those characters. So that H and then AE LLO, that would match the word hallo. So in other words, the German word for hello. It would match the English word hello, and so on. Okay, so different wildcards that you can use in your find command. You can pass to iname or to -name. If I wanted to find all directories under /etc that contain the word net, so I'll say find /etc where I want to start the search, type D, so we want directories now, and we'll say iname star net star. So any directories that in their name they include the substring net. Now, I'm not logged in as root right now, so most of those are permission denied, but you can see it did find a few: etc systemd network, etc network manager, and so on. This is a useful one. So finding all files that were modified in the last 5 minutes. Sometimes I'll run a command and it's not clear what it did. You know, did it do anything? Did it write data anywhere? What just happened? And so what you can do is run find and find all files that were modified in the last minute or the last 2 minutes. So as an example here, if we wanted to find all of our log files on the system that were modified in the last 5 minutes, I could say find in var log, type F, cmin -5. And that will say in the last 5 minutes, show me all files that were modified in the last 5 minutes. And you can see things like the main log file, var log messages, for example, any files modified in the last 5 minutes. Again, I said we can use find to find files of a given size. So I could say, okay, I want to find all files that are greater than 100 megs. I can use that plus 100M for megabytes. We could use K for kilobytes, G for gigabytes. So this command can do a ton. If you want, you can take a look at man find or Google it or ask ChatGPT, but it can do a whole lot. It's a very powerful command, very, very useful. It's worthwhile spending some time getting to know this command. I use it all the time. Okay, so moving on to dot files. So there are a few special files that, and we've already talked about some of these, but when you log in your home directory, you'll see these files that are colloquially known as dot files because they start with a dot. So again, we do an ls-la or a -a, and we can see, okay, we've got this bash history file. So this contains a history of all of the commands that I have run. Every time I log out, all of the commands I've run in that session get saved into the .bash history. And that allows me then to look up a previous command. So we're going to see in a later topic, there is a history command, and it reads from that bash history file. Okay, so that is your bash history file. There are also these bash profile and bash rc files. These are startup files. So when you log in, these files get executed. Not super important, the details, but bash profile, it gets executed when it's a login shell. So when you're logging into a computer, for example, or when you SSH in, that's called a login shell and it gets executed. Bash rc gets executed when it's a non-login shell, essentially. However, you will see, if you look at bash profile, for example, it executes bash rc. So bottom line is, if you want to add commands that get executed when you log in, add them to bash rc. Okay, so if we take a look at the bash rc file, you can see it's got a bunch of aliases. So if you had followed in topic 1 my advice where I said, okay, set up those aliases for like to alias rm to rm-i and mv to mv-i so that they will confirm things. That's where you would put your aliases in bash rc. I don't know, I can add other commands. So if I want to say like, hey bro, when I log in, and now it greets me in a very casual manner. Okay, so that's the bash rc file. There is bash logout. So again, if I wanted to for whatever reason, execute commands when I'm logging out, I can do that as well. So we can say, peace out. And there we go. Super useful stuff. Okay, so that's the bash rc, bash logout. We talked about git config. So when you ran like git config -- global, user.name, Jeff Shantz, blah, 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 that gets written into your home directory into a file .git config. So if you needed to edit that manually for whatever reason, you can edit it in there. And then in the editors topic, I talked about nanorc and vimrc as being configuration files for the nano and vim editors, respectively. So just about everything is valid in terms of a Linux file name, in terms of what characters you can put into them. They are case sensitive, so capital A.text is completely different from lowercase a.text. They can exist in the same directory, no problem, as two separate files. So as I say, just about any character goes. Of course, you can't have the path separator, the /, because that is used to separate the components of the path. I don't know why you would, but you can't have the null character either in your file name. If you use basically any of these characters that you see, you're just inviting trouble. You're going to get yourself into, it's just going to be a pain for you. So just avoid those. Stick to regular like letters and numbers and underscores and dashes. Yeah, definitely don't do something like tilde as the first character of your file name. So I don't know, if I were to create a file, I would have to quote it, but if I were to do something like this, now I've got a file called ~jeff. And if I accidentally say, I want to try and delete that, and I say rm-rf ~jeff, what's that going to do? I'm going to blow away my home directory, right? So just don't put things like tildes and characters like that into your file names. File extensions, we already talked about this. Linux doesn't really care about file extensions. It doesn't care like Windows does, where it wants you to have a specific file extension for each file because it uses that in, for example, Windows Explorer to show you a particular icon for the type of file that it is. And if it's an executable file, it wants it to be .exe, for example. Linux doesn't care. All of those are legal file names. So I can just have A without an extension. I can have A dot, A, A.B.C, where I've got multiple extensions. That's all fine. Linux doesn't care. Having said that, we do typically use extensions anyway, just for our own purposes, for clarity, so that we know what kind of file it is. So JPEG for JPEG files, text for text files, and so on. And some applications like GCC will sort of enforce or expect certain extensions. So GCC expects that your C code is going to be in a .c file, that your header files are going to be in .h files, object files in .o, and so on. But for the most part, Linux doesn't really care about file extensions. Okay, we've got some generous limits on length. You can have file names up to 255 characters. The entire length of your path, starting from the root directory, can be 4,096 characters, so you're probably not going to run out of space there. And then, as I say, on Windows, for executable files, you've got a special extension, .exe. On Linux, you don't have to, right? It could be anything you want, or it's often just no executable whatsoever. You can see, if we look at user bin, those are all executable files. None of them have extensions. I'm not running, the command ls.exe or cp.exe. I'm just running ls. I also cannot, like in Windows, if you have a file called a.exe and I'm at the DOS prompt and I want to run that, I can just type A and Windows will know, okay, you want to run a.exe. I can't do that on Linux. If I've got a file called a.exe, I have to run it with // and then the full file name, a.exe. Now sometimes you've got binary files on your system and distinguishing them, like is this an executable file or is it just some binary data file? I don't really know what it is. You can use the file command for that. So let's take a look. If I were to look at, say, user bin ls with file. So that gives me a long-winded reply, but you can see that it says it's an executable file. So that tells me that is a program that I can run. If instead I were to look at, I don't know, like let's say a library, like user lib64 libc.so.6. So the C standard library. Again, lots of output there, but you can see it says shared object. It doesn't say anything about being executable. Okay, so I know that that's not a program that I can run. And you can do it on other files too. I could do it on, say, hello.c. That tells me it's an ASCII file, it's a text file, and it's C source code. I don't know, do it on my socket file. Tells me it's a socket. Thanks, Captain Obvious. Okay. So if you're not sure of a file's type, you can run it with the file command, and that will give you some information. Now, I like this one. I always see this with beginners to Linux. You get yourselves into trouble. I don't even know how you do it. But I will sometimes tell you, type ls when I'm helping you out, and I'll see things like this. So let me just create a temp directory here. So I will see that someone has accidentally, I don't know why or how, but maybe they've, oops, for whatever reason, they've done something like this, where they've managed to get a file named -i, for example, in their home directory. And sometimes it just makes me chuckle. Sometimes, I'm not making fun of you, but it's just kind of funny. I'll tell you to type ls, and you'll have all of these weird file names that you've been, testing out different commands, and for whatever reason, you manage to get these weird file names into your directories. Now, the problem, of course, is if I try to delete this, RM is going to think that I'm saying rm-i, right? I'm passing the option -i to rm. And so if I try to delete that, it's going to say, wait, you didn't tell me what file you wanted to delete. It's thinking I'm saying rm-i, right? Interactive mode, confirm that deletion. And it wants me to specify a file name. Well, -i is what I wanted to delete. So the way you can get yourself out of that situation, a lot of commands will support --, which tells it there are no further options after this --. So I can say rm-, now I can say -i, and that will then actually pass -i as the file name to rm. And a lot of commands do accept that. So if you find yourself in that situation, just put a --, and then you've got your -i for the file name. Okay, and we looked at the file command to determine the type of files. So wildcards are special characters that we use to either stand in for longer sequences of text. So I can type a very short sequence and use that to represent a longer sequence. Alternatively, it can stand in for multiple sequences. So I type a wildcard so that I can represent multiple file names, for example. So the main wildcard characters that you will be working with at the Linux shell, first of all, the asterisk, so the star, will stand in for any sequence of characters. So if I have something like h*o, that's going to match file names like hallo, hello, hullo, h.o, right? Anything that starts with an H and ends with an O. Single character is represented by the question mark. So if I do H*LLO, then that's going to stand in for, or it's going to match hallo, hello, and hullo. Okay, so a single character. If I put characters between square brackets, so the third line there, so here I have H and then A and E in brackets, that's going to match either of those characters. And I can put as many of those characters in those square brackets as I want. Okay, so in that case it matches hallo and hello, but not hullo because I don't have U in there. If you have a lot of characters in a row, you can actually use a range. So the fourth line, where I'm saying A to D, for example, and that will match the characters A to D. And again, you can have any number in your range. I could have 0 to 9, I could have A to Z, capital A to capital Z, and so on. And you can have multiple ranges. So I could say A to Z, lowercase, and then A to Z, uppercase. You can put that in the same range. So in this case, we've got B and then A to C, which will match BA, BB, and BC. And then finally, the curly braces allow us to match specific substrings, specific terms. So this example, T1, T2, T3, that has 3 in it. Again, you can have as many as you like in there. So in my example here, we've got AN and UN. and that's going to match BANK and BUNK, bank and bunk. Now, when you type wildcards at the shell, before the shell actually executes the command that you're trying to invoke, it will expand the wildcards, and the command is going to actually receive the result of expanding the wildcard. It's not going to receive the wildcard itself. That process of expanding that the shell does is called globbing. And the advantage there is that when I write a program that takes command line parameters, my program does not have to worry about, oh, the user might type a wildcard. They might use a star or a curly brace or whatever. My program just knows that the shell is going to glob any wildcards that the user types, and therefore simplifies things for me. So as an example here, if I type something like lsp star, and you can see all those file names there, ls is not receiving that p star. It's actually receiving the expanded, the globbed result of that wildcard. So it actually receives what you see on the right side there, those 3 arguments. Taking a look at some examples, if I wanted to match all text files that begin with p, I would say ls p star and then .text. So all files that begin with a p and are text files. So p star.txt, and of course then that matches all of those. If I wanted to match all files that end with mp and then something, I can say star.mp and then something. So we said that the question mark stands in for a single character. Okay, and then that gives me, for example, an MP4 file as well as an MP3. If we want to match all PDF files that have A or E as their second letter, so I would want to say, all right, anything for the first letter, we would have A or E as the second letter, so in square brackets, and then star, and then .pdf. Okay, and this has an E as its second letter, an A, and an A. And they all end with PDF. Matching all files that start with A, B, or C. So I will say in square brackets, remember we can do a range. So I could say ABC like this, or if it were a long range, I could say A-C, and that works fine. Now, if you need the dash, if you're trying to match that character, you have to put it either at the start of the range or the end. So, I could say like A dash, and that would match either the character A or the character hyphen, dash. Alternatively, I could say dash A, and that would also match it, okay? Matching all text files that contain AN, EN, or RI. So I'm gonna say, all right, we want something that contains these substrings. So it can start with anything. It could contain AN, ER, or RI. And then it can end with anything, and then .txt we said. And so here we have, all right, this has RI in it, this has ER, AN, and ER. Okay, similar example, match all HTML and PDF files that contain the substring ER. So again, substring, but we only have one substring here, so I'll just say star, ER, star. So anything, and then ER, and then anything. And the star matches 0 or more characters. So it will match if the string starts with ER, for example. Having this star here, it'll still match. Okay, so we're saying star, ER, star, and we said we want it to end with either PDF or HTML. So dot, and then in curly braces, PDF or HTML. So we've got er.pdf, er.html, er.html, and er.pdf. Okay, these aren't really gotchas. They're just a few things to understand. Wildcards will not cross directory boundaries. So if I have, for example, let's say a directory 1, and I've got a file ABC in there. Okay, so if we look at the contents of dir1, it's got ABC. We'll say we've got a file ABC in this directory as well. If I do, for example, lsa star, that shows me my ABC in the current directory, but it does not cross into directory 1, into dir1 to show me that ABC. Okay, so wildcards will not, by default, cross directory boundaries unless we ask them to, unless I were to say, ls dir1 /a star, Or if I wanted to see all files that start with A in the current directory and in dir1, then I would just pass both to ls. So I would say ls a star and dir1 a star, and then that'll show me both. But by default, if I just use a wildcard, it's only matching in the current directory. Wildcards will also not match a leading dot. So if you go to your home directory, for example, and you take a look at your dot files. So we talked about these, bash history, bash logout, and maybe you want to see those. So you might think that you could type something like ls star bash, and it says it can't access them, because by default a wildcard will not match a leading dot. So it will not match a leading dot at the beginning of a file name, and it will not match a leading dot after a slash. So I can't say something like this either. That's not going to work either. Okay, so if I wanted to see those, I have to explicitly say something like ls dot, bash star, and now that shows me. Okay, some more advanced examples. So take a look for a second at the first example there, ls/bin/star, and then we have the dash and the underscore and then star. Anybody want to take a guess at what that will match? So we're saying bin, star, we've got the dash and the underscore and then star. So I'm saying anything in the bin directory that starts with something contains either a dash or an underscore and then ends with something. Okay, and so then you can see we've got all of the commands here that either have a dash in them or an underscore. Okay, ls star. So this one is kind of surprising sometimes to people who are new to wildcards and globbing. So if I type ls in my home directory, that's what I've got, right? And so if I were to type ls star, I'm thinking, okay, it's just going to show me the same thing, because that matches everything in my directory. But what it actually shows me is, okay, it shows me all of the files that are in that directory, so my hello.txt and all of those, but then it shows me the contents of all of these directories as well. So the reason for that is, remember, we talked about globbing. So the shell will glob all of your wildcards. It will expand them and then pass those to the command that you're running. So when I type ls star I should say, what it's actually running is it will expand it to all of my file names in the current directory, and then it will expand it to courses, Git, lab 5, laptop, lectures, blah, blah, blah. All of those files will get passed to ls. So then ls is saying, okay, you want me to show you all of your files in the current directory, and then you want me to list the contents of the courses directory and the Git directory and so on, and that's why it gives us that output that we saw. Now, this one is also surprising, especially if you're familiar with the DOS prompt on Windows. This will actually work, so this will allow you to rename a set of files from one file extension to another. On Linux, this does not work. Okay, so if we have a set of so you'll notice that I'm using a wildcard here to create 6 files, f1 to 6.txt. Okay? So if I wanted to move those, I might think, or if I wanted to rename them to .txt, I might think I can do this. But move is saying, okay, I don't know what the target star.txt is. Now the reason for that, again, is globbing. So what's happening here is that to move, the shell is expanding that wildcard, so it gets f2.txt, f3.txt, f4.txt, f5.txt, f6.txt, and then it tries to match star.txt, which in this case doesn't exist. But let's make one called file.txt, and let's see what happens now. It says not a directory. So back in the day, what would have happened was it would have expanded the star.txt and star.txt, and your move command would have looked like this. And basically what would have happened is all of your files would have been deleted because they would have been renamed to file.txt. Now move's a little bit smarter. It sees, okay, you're trying to rename multiple files. but you're trying to move them into something that is not a directory, and so it won't let you. It won't let you overwrite that file. Okay, so the bottom line is if you were trying to rename multiple files, you have to do it a different way, like a shell script or a little one-liner. You can't do it just by simply saying move star.one extension to star.another. Okay, wrapping up with quoting. So when you put text in double quotes, it will stop the shell from interpreting some special characters. So it'll stop it from interpreting white space, characters like star and tilde, those will be stopped. So as an example here, we've got echo, and we are typing a bunch of spaces between our arguments. But when echo actually prints it out, it gets rid of all that space, because the shell is just removing those spaces. Echo is receiving, in this case, 4 arguments, the arguments A, B, C, and D. The white space is ignored. Now, if I wanted to preserve that, I can put double quotes around it. In this case now, instead of receiving 4 arguments, echo is only going to receive 1 argument, that string. Okay, and now that space is preserved. Same thing with, if I were to say ls tilde, for example, that shows me the contents of my home directory. If I wanted to, for whatever reason, say echo tilde, I should say. So let's do this. Echo tilde, right? That expands it. If I put it in quotes, then I get the actual tilde character. Same with spaces. So if you want to make a directory with spaces, I don't recommend it because it's just a pain to type, really. But what you could do is, okay, put it in quotes. And now you've got a directory name that has spaces in it. It's a pain because now you have to either escape it. We're going to see escaping a space with a backslash in a few minutes. Or you have to put it in quotes every time. So it's just kind of a pain to type when you're at the shell, but if you like that, then go for it. Environment variables are also still evaluated within double quotes. So last day we learned about the home environment variable, how the shell maintains this for everyone, and it always contains the path to your home directory. So if you put this in quotes, my home directory is home, it will still be evaluated within double quotes. Now, single quotes stop the interpretation of even more characters, or most characters even. So if I were to type something like, I don't know, for whatever reason, exclamation mark 1, 2, 3. You see that it says, oh, echo get pull. The reason is that's a special character. We're going to see when we talk about history later in the course. This pulls up command number 123 from my history, from my bash history, which in my case happened to be the get pull command. So if that's not what I wanted, I could put that in single quotes. And then I would actually stop the interpretation of that special exclamation mark. Same with environment variables. So again, we said, all right, if we put an environment variable in double quotes, it'll still be expanded. If for whatever reason I need it to be shown without being expanded, then I can use single quotes. Okay, backticks. Backticks will execute whatever command you put within them and then return the result. So I could say something like, my username is, and then in backticks, I could say, who am I? Okay, backticks are the key to the left of your 1, in case you're wondering. Okay, so that then runs the command and then it inserts it in that string that I passed to echo. So they're useful in shell scripts. On their own like that, you might be thinking, well, why would I want that? But you can do something like this. So we'll talk about this when we talk about shell scripting toward the end of the course, where maybe I'll want to store the current date in a variable here called current date. And then later on, I want to print out the value of that. I can do that with backticks. Now, one thing to note is that backticks do work, and as far as I know, they will continue to work, but that notation is considered deprecated. The recommended notation to use now is $, and then parentheses. So my username is, and then in $, parentheses, who am I? Okay, they do the same thing. They execute a command, return the result, but this is now the recommended notation. Okay, so I mentioned backslash a few moments ago. It's used to escape the next character. So if I've got this directory with spaces here, I can say, I can't just say dir with spaces, that's not going to work. I have to escape each one of those with a backslash. Okay, same with, I can't say like make dir with spaces, because that's going to make 3 directories, dir, with, and spaces. Oops. Okay, but if I wanted to make a directory with spaces, I can say dir and then escape each one of those spaces. That works fine. Alternatively, if I wanted to, for some reason, have weird characters like stars, I can escape each one of those, and that will tell the shell not to interpret them. Don't do that, obviously. You don't want to put weird control characters in your directories, and definitely don't do something like this, where you say something like, I don't know, I make a directory called ~Jeff. And now I'm gonna, without thinking, I'll type something like this and I'll blow away my entire home directory. Okay, if I actually wanted to delete that, I would put a slash in front of that. And now I haven't blown away my home directory, I've just blown away the directory called ~Jeff that is in the current directory. So, moral of the story is, it's just best not to put weird characters like that into your file names. So you can use the backslash to escape quote characters. So I can say something like, if I want to actually display the double quotes, I'll say something like this, Westerns, Faculty of Science, and then that actually displays those quotes rather than using the quotes to stop interpretation at the shell. And then finally, I can use it to escape a new line. So if I have a long line, this is a really long line of text. I can have a backslash, and you can see the shell character, the prompt character here changes to let me know that it's a continuation of that string. And I am resuming this string on the next line. Okay, and it just then concatenates the two together. Okay, last one for quoting is Control-V. So this is not used all that often, but every now and then there's a case that arises where you kind of need this. It allows you to input kind of weird stuff at the command line, like non-printable characters and control characters. So as an example, and this is kind of silly because you wouldn't do this, but if I wanted to have, so first of all, let's just create a file there. If I wanted to have a file that had a tab in its file name for some reason, if I type, for example, touch H and then I press tab, we saw already in topic 2, or topic 1, I guess it was, tab completion, right? The shell tries to complete whatever I'm typing when I press tab. If I wanted to actually put the tab character in there, I can press Control-V and then I press my character. So then I press tab. And then that actually puts it in there. And now you can see if we type ls, the way it shows it is kind of a strange notation, but this is basically H plus a tab and then lo.text. So don't do this. Obviously, that's not a good thing to do, but as I say, occasionally a situation arises, for example, where a student has gotten themselves into trouble. You know, it's a beginning Linux student, and sometimes I mentioned last day that I will tell them to type ls, and whatever commands they've been executing, they've accidentally managed to create these weird file names. Sometimes you have to use Control-V in order to get rid of some of those weird ones. Just another quick example, again, very contrived. I don't know why you would do this, but the backspace character. So I could say, okay, H-A-L, and then, oh, I meant to write hello. So I could put Control-V, Control-H, which is the backspace character, Control-V, Control-H, and then E-L-L-O. And then instead of the German version of hello, we have the English version. So it actually does 2 backspaces, and then it prints out the rest of the string. Again, you would never need to do this, but just an example of how Control-V works to insert control characters at the shell. Okay, so we saw inodes. We saw how every single entry in the file system has an inode, saw the different types of files, directories, links, and so on, FIFOs, sockets. We took a look at the file system hierarchy. So what are the standard directories, what they're for. So the unified file system, how things are mounted. The df command not only lets you see disk free, so how much space you have left, but also lets you see your mounts. Most of the path stuff was review. We did see the home environment variable, which stores the path to your home directory. So took a look at hard versus soft links with the ln command. So ln creates a hard link, ln-s creates a symbolic link. And we saw how they differ. The hard link, the two names point at the same file on disk, whereas a symbolic link, the link points at another file name or another path within the file system. Saw some examples of using the find command to find files and directories. We looked at dot files, bash history, bash rc, and so on. Linux file names, so what are the valid characters? And then we talked this morning about wildcards and globbing and quoting. So I've got a little cheat sheet there for you again. You can take a look at that as you are studying. So that wraps up Linux files and directories.